Hello everyone, welcome to the next video on ABC to dq0 transformation, simulation of ABC to dq0 transformation. In the last video, I have shown you how to create this power circuit, how to add the measurement block, how to connect these two sources and load to the respective buses. Now we have VABC B1 measurement is at this bus and IABC B1 measurement as at this bus. Okay, so I need the phase information from here, so I will change this phase to phase instead of phase to phase as a phase to ground. Okay, and one more in this also I will change it to phase to ground, and in this also I need this information from phase to ground. Okay, so and how to plot the VABC and IABC I have shown in the previous lecture. To convert ABC quantity into dq0 quantity, we need this sum block, which is a PLL block. This block is a PLL block. Then ABC to dq0 transformation block. Okay, then we need demux, and then we need one mux. So first, frequency information of the given waveform is very important. So what I will do, I will extract the frequency information. I have to give the one signal to here, but here we have in VABC the information of A phase, B phase and C phase is there. I want to separate out this, so I will connect this block here, and demux outputs I will set to 3. So now in this first block VA is available. In the first output VA is available, here VB and here VC. Out of that VA block I will connect it to the PLL block, and output of this PLL I want to take omega t as the output. So I will connect one go to block. Okay, go to block, I will take one go to block here. Let it appear, go to block, and I will connect this omega t to go to and rename this a go to block. I will double click to this go to block. Okay, let me close the previous sum window which was open. Okay, so I will change this block is as omega t, and tag visibility you keep it on global. Okay, so if you keep a local, it will work only for the simulation window. If you have a subsystem, then it will not work. So always keep this on global, so that in that simulation wherever omega t is required, it will become a global variable. Okay, so okay, wait, now it is responding. Okay, so omega t is created here. Okay, let the name come here. Hmm. It is taking time, wait. Okay, the omega t is appeared here. Now this omega t is required in ABC to dq0 transformation. In ABC to dq0 transformation, first we have to give the ABC quantity. So first I will connect this ABC quantity, then here I need the omega t. So I will take from block. Okay, from block, it will, I will connect here, and here I will update this tag as omega t because I need the omega. Okay, so automatically this source tag is coming here. Now here I am getting the information of dq0. That dq0 information is here. So dq0 information I need to separate out. So I will connect the demux block over here. Okay, demux block. Then let's see on the scope. So double click the slope scope. Wait, it is coming. Okay, okay, so let me take this scope block again here. So I will double click to this window, and I will take this scope block once again. Previous scope blocks was giving some error. Okay, so this scope block, I will open its properties. Double click, it will open its information window. Okay, this information is now here. Click on setting. Here I need four outputs. I will click on layout and I will copy this four. I want this is in this format. Okay, layout is one column layout. To this scope window, I will connect the VD over here, VQ and V0. So I can give this name as VD. Double click on this line VQ and double click on this line, it is V0 information. I want give the VABC input here. Either you connect it from here. Okay, you can connect it from here for the measurement purpose, or you can give by the tagging also. You can copy this from block and you can connect directly to here. Okay, so now let's run this. Let's check whether this is performing or not. So here you can check PLL block minimum frequency. I'm taking the minimum frequency as a 35. Okay, 35. I want the frequency output of 50 hertz because my signal is of 50 hertz. Don't change this regulator gain. Keep KIP, KI and KD as it is, and filter out information. Filtering coefficients, I will give this filtering coefficients to 5. Okay, 5 hertz only filtering. It will only give the low frequency signals will be cut off from the signal. Okay, so this is setting. Now here you can observe, here it is given as uh, rotating fray aligned at omega t is equal to 0, that are 90-degree phase A or aligned with phase A. So 90-degree lagging to the phase A means q axis is lagging to 90-degree with the phase A, it is given here. Now let's run this simulation. Okay, the simulation is running. Okay, it's running. Wait. The simulation is completed. If I double click to this, so you can check here, uh, click this here. Okay, let it is coming. Okay, let's run the file with stop time as a 1 second. So stop time is given as 1 second. I'm running this file once again, and I'm opening this scope. So you can observe here, you can adjust the scale by using the right click, configure parameter. Y limit minimum is 0, highest is 500 kilovolt. So 500 e raised to 3. I can give this name. And if you observe this output, so let me check with the small scope here. Okay, so let me zoom this much. So if you observe here, this value is almost constant to the 4, uh, almost constant to the 4.54. So there is small variation in this VD, but VQ value is almost 0. means quadrature axis component is 0 and 0 axis component is also at 0 volt. It is depending upon the largely depending upon the omega t information which is coming from here. So here I can change the sum value such that it will give the information good. So let me check it with the filtering frequency as a 25. Okay, and let's run again. Okay, so again it increases the value. So again we will make this tight, so I can keep this frequency to the 1 hertz only, but response will become a slower. Cutoff frequency response will become a slower. Okay, so by this way we can simulate the systems. This is AP0 to DQ, ABC to DQ0 is converted here. Similarly, we can give this statement to the current. So I will copy this block. Okay, this block, control I will place in. Okay, so these three blocks I will copy and I will paste over here. Okay, now here I need not to extract the omega t information again. I will connect this to the current. Okay, and scope I will take here. The current information IABC is here, then ID, then IQ, and then I0. So you can change this name as ID, IQ, and I0. Okay, so double click this block. Here I have changed the axis property. Okay, axis property are again restored here. Need not to worry about axis property. Then again you run this file. So now it will convert your currents into the ABC value. So currents into, why it is coming VABC here, because this name I have not changed. This is the IABC in ampere. So IABC in ampere. Okay, once again I will run it. Okay, so here you will get the information of ID, IQ, that is direct axis current, quadrature axis current, and zero axis current. So zero sequence current is not present here because the system is a symmetrical in nature. So that zero sequence current is not present. Now what we can do with this simulation, I want to calculate the active and reactive power using the dq0 transformation. So to calculate the active and reactive power from using the dq0 transformation, first see the formula of active power. The active power is calculated as Vd minus Vd into Id plus Vq into Iq. Okay, so we want to implement these functions. So let me rearrange this into small size. Okay, so here I can create one area. Here I have converted the voltage and current into the dq0 transformation, and now system is locked in this area, and here I can give this name uh, ABC to dq0 transformation. That is done. Okay, this then documentation is very important while doing this simulation, so that it is easily understand whenever you open this file once again. Now I want to convert, I want to take from this what I need the active and reactive power calculation. So again I will add one from block, go to block here, because I need VD VQ this information. So go to block is added. Just a minute. Okay, this go to block is added over here. I will click this, connect this go to block here, and I will give this name as VDQ0. In this VDQ0 information is there. I will make it I will make it global. Apply. Okay, then similarly I need the current also. So same block I will drag, I will connect this here. So and I want to change this as the ID 0, IDQ0. Okay, Now here vd0, vdq0 and idq0 information is available. Now I will take the go from block, from, double click to this, and I will change this is to the vdq0. Okay, that tab will updating the tab. Okay, and similarly here I have idq0. I will take the block of demux. I will connect this two block. So what is available here? Here VD is available, here VQ is available, and here V0. Here VD, VQ, V0. But keep in mind, V0 and here VD, VQ, V0, ID, IQ, I0. So V0 and I0 are the zeros value because our system is symmetrical. So need not to worry about this in this simulation. Now I want the active power. So active power. Okay, so what is the formula of active power? Let me write down in the form of text over here. So I will insert the text. uh, Active power formula is vd id plus vq iq. Okay, this must be multiplied by 3 by 2 to get the 3 phase power in dq transformation. This is the formula which is given in the information uh, provided on a website, on my website link it is available. Why this is equal to this value. Then reactive power, how we will calculate reactive power formula is vq into vq into id minus Vd into Iq, cross multiplication of the voltage and current multiplied with 3 by 2. This is my reactive power. Okay, so this formula is to be implemented now. So I need a product block. So double click here. I will take the product block, product. Then Vd is connected. Then it is multiplied with Id. Second block, VQ is connected and it is multiplied with IQ. To get the reactive power, VD multiplied with, sorry, first is a VQ, no? Okay. Let's think about the reactive power later. First we'll complete the active power. Then you click the block of add. Okay, so you add these two. If you add these two, then we have to multiply it with 3 by 2. Then take the block of gain. So in the gain, add this gain to 3 by 2. We connect this gain block at this output, and here you will get the active power. Now how to get the reactive power? Okay, take the two product block VQ. This is the my VQ information. VQ is multiplied with ID. Sorry, VQ is multiplied with ID, and VD is here. So VD is multiplied with VQ. VD is multiplied with VQ. Again I have to this add, and these two blocks are needed. So I will connect these two blocks here. Okay, so let me double click here. Then okay, so this information, then I will connect one more scope at this window. Okay, I need to measure the active and reactive power. Again I will set the number of axes is equal to 2. Layout is like this, apply. Okay, then come here. You can align the block so that measurement process will become simpler. So in this block I am getting P in terms of watt. Okay, and here I am getting Q in terms of VAR. Okay, so now this is what active and reactive power calculation. I will take another area. Okay, I will create one area over here for my understanding. So we have implemented this equation for active and reactive power. This is what active and reactive power calculations. Okay, now I don't need this V0 and I0, so you remain as it is. Keep it as it is. Now let's simulate this circuit once again. Hmm, okay, so here you can observe uh, active power is almost 2.17 into 10 raised to 2.14 into 10 to 7, means 214 megawatt power, and reactive power is 4.1 approximately. So you can change for better visibility, you can change this access setting. Y minimum is 0, and keep, okay, or again I will change y minimum is 0, and you keep this is 21, how much it is coming, 217 megawatt. So you keep this 300 e raised to 6. Okay, so you can see this active power. Similarly, I can configure this parameter with this axis as a 0, and it is almost 500 MVR. So I'm keeping this 500 e raised to 6. Apply. Okay, so this is the calculations of active and reactive power from the dq0 transformation. Okay, so hope you understand this topic, how to convert abc to dq0, how and how measure the power in the circuit. Thank you. If you like my channel, please subscribe.